There are many applications for roll alignment in industries such as pulp and paper, printing, steel, plastic, aluminum manufacturing, as well as textile and rubber industries, just to name a few. Rolls must be parallel or level in the vertical plane up and down as shown in the side view of the rolls in the top graphic. They also need to be parallel in the horizontal plane, side to side, as shown in the lower graphic. To accomplish this, you need the right tool. The Easy Laser E970 uses the same traditional method as optical tooling. However, instead of using a scope and a target, a laser transmitter and a measuring detector is used along with some other bracketing. With the display unit, everyone can see the results. This eliminates the guesswork. To make it easier, the rolls are all adjusted live time on the screen, giving confidence in your results. The bulk of the work is measuring the parallelism of the rolls in the horizontal plane. There are two ways to accomplish this using the E970. The first is to use the monuments or plugs in the ground beside the machine as reference points. These monuments were used to build the machine in a straight line during construction. Once you set up the D22 laser along the reference line, you can then move the angular prism, which deflects the beam 90 degrees along each roll to check for parallel. The other method is to use one of the rolls as a reference, or you can even use 2 points on the machine frame. To give you a quick understanding of the process, we will demonstrate this using our own simple frame and roll setup. To start, we will check the vertical measurements of the rolls we want to measure. With the digital level included in the system, we can decide to mount it directly on the roll or by using the included bracketing for larger rolls. You can check the level value of the roll using its own LED display or by using the values program on the system's display. Make sure the level is at its apex of the roll using the side-to-side inclinometer, which should be at or close to 0 degrees. The result along the length of the roll is 13 thou per foot of angle. We know the length of the roll, so a simple calculation tells us the amount of shim that we can add or remove as necessary. After we make the correction and tighten the roll down, we place the level back into the same position, and as you can see, we have 0. This result can be recorded here or when using the roll program. For the horizontal measurements, we begin with the D22 laser transmitter. Here we have it mounted on the sides so the beam can sweep the floor. It is attached to a sliding table that allows for horizontal adjustments by turning the wheel and is also on a geared tripod which allows for vertical adjustments by turning the crank. There are 3 precision levels in the unit. For this application, we only need to level this one, which is easily adjusted to level with the coarse and fine adjustment screws. A laser beam can be projected from the turret so that it can sweep a complete 360 degrees. It can also be switched and point 90 degrees to the sweep using a prism mounted in the turret. Here we sweep the beam to a simple red target that we use for roughing in. Our goal is to put the beam into the vertical slot in the target. If we take a closer look at the back of the target's bracket, you can see it has a center locating pin. The pin is placed into a floor plug or monument which looks something like this. If we look straight down on the target's bracket, we also see a level. When adjusted, we know that the slot in the target is vertical. This graphic illustrates the way we have set up the D22 laser and the 2 targets in reference to the rolls. The target can also be placed on either side of the D22 laser as shown in light red, which can be the case in some instances. This depends on where the monuments or plugs are located. For the near target, we adjust the offset of the D22 by turning one of the wheels on the sliding table so it drops into the target's vertical slot. When you see a hint of the beam on both sides of the target slot, you know the beam is centered. Next, we point the laser to the far target. We adjust this into the target's vertical slot by turning the tripod swivel, which is the angular adjustment. We repeat these last two steps, adjusting the angle and the offset until the beam is in the center of both slots. Each application is different, of course, but the whole rough-in process should take about 15 to 20 minutes. To explain further, we use the same illustration. What we have done is projected a laser beam down the length of a machine which is parallel to the machine but perpendicular or square to the rolls. We use the two floor plugs as a datum line. The beam is now centered on this line and the beam becomes the reference line. This is what we measure from. For many applications, for example a long conveyor line, this is all the setup you would need. Other roll alignment applications may need more accuracy, such as a printing press. To do this, we replace the roughing in targets with a different self-leveling mounting bracket and detector. First, we place the mounting bracket pin into the punch mark made in the floor plug. We then level the bracket using the attached levels and adjusting screws. The measuring unit we are using is a dual-axis detector, meaning it gives us a live time value in both the horizontal and vertical planes. In this case, we are using an M-unit detector, which also gives us the capability to do shaft alignment if we wanted. Using the plastic grid target is a great benefit when doing any rough alignment. We plug in the wireless unit into the detector and a light will indicate that it's on. Once we place the detector onto the rods, we can adjust the detector in one plane and the D22 laser in the other plane, so the beam hits the center of the detector. When ready, we remove the target and can see the laser dot position on the display screen. At the top of the screen, we can see the live time values. To create the first reference point, we press the 0 button and zero the values. Now we move the whole bracket and detector setup to the far foot plug and set it in place. We sweep the beam over the floor into the detector's red target. Once we take the red target off, we can see the result on the display. We can now adjust the D22 tilt table using the coarse and fine adjustment screws. If you look closely, you can see the live vertical or V value coming down to 0. It's important to note we are only working in the measuring unit's vertical plane still, as the detector is on its side. To get the horizontal value to read 0, we would adjust the laser turret to the center of the detector. Our goal is to get the beam to read 0 at both points, which will give us a very accurate reference line to measure from. Once we get it to 0, the next step is to turn the D22 turret so that the beam is in a horizontal plane. This is all the adjustment the D22 needs and is now locked in place. What we have now is a laser beam running down the length of the machine that is more accurately perpendicular or square to the rolls we want to measure. We are now ready to place the angular prism in the path of the laser, which will deflect the beam 90 degrees and allows us to measure and adjust the roll. The angular prism is mounted on a sliding table, which is mounted on a geared tripod. This allows us to adjust the prism up and down or left and right in a controlled way, so that we can rough in the beam to the center of the target in the prism. Before we do this, we want to make sure that we have properly positioned the prism opposite the rolls we want to measure. In this demonstration, I can measure both of these rolls from this one setup because we positioned the prism roughly between the rolls. To set up the prism directly in the laser beam's path, we slide it across on the sliding table so that the beam is under the center of the prism target. Then we lower the tripod and the beam hits the center of the angular prism's target door. When looking at the front side of the prism, you can see one of the two locking screws on the side, and above the red target door, you can see the adjustment screw for fine beam adjustment. This pentaprism has its own tilt table used for bucking the beam in, which we will demonstrate next. The two rods in the front of the prism are for mounting the detector, which we will do a bit later. The center of the red target door is a small mirror, which is a very clever way that speeds up the bucking in process. This mirror is reflecting the beam back to the D22 aperture, where the beam originates from. You can see the red dot on the side of the D22. To properly mount the angular prism and buck in the beam, we can place this target on the D22's beam aperture. This reduces the size of the beam to a small dot. The angular prism's tilt table controls allows us to adjust the reflected beam. This one adjusts the angle left and right. And this one up and down. When the beam disappears into the aperture, the prism is aligned. This simple process saves us a lot of time. For many other systems or equipment, this process can take hours, while we do it in minutes. If we want even more accuracy, we can mount the detector in front of the prism. To start, we can rotate it down to what we call the 6 o'clock position, or 180 degrees of inclination. To see the built-in inclinometer value, we zoom in and it shows us that we are 179.8 degrees, which is close enough to 180. We then zero the live time values above and rotate the detector back up to 12 o'clock, or 0 degrees. Because we used rotation, we have to halve this value by pushing the half button. Now we can adjust the detector using the prism controls and live time and watch the values come to 0. First, the horizontal value, which is on the right side. Then the vertical value, on the left side. After we remove the detector and open the target door, you can see the beam on the back of the hand. This projected beam is perpendicular or 90 degrees to the reference line we set up using the floor monuments and detector. We are now ready to measure the horizontal plane or parallelism of the rolls. To do this, we can use the magnetic sliding bracket. It has two magnetic clamps and sits on the roll using the 4 cone mounts. These mounts are adjustable for different sized rolls and they centralize the detector on the roll. We add 2 rods to this bracket onto the turnable head and clamp it on the roll. The detector is mounted on the bracket and is lowered into position so that it is roughly at the 90 degree or 9 o'clock position. We loosen and slide the detector so that our projected beam hits the center of the target. Then we remove the target door and turn the detector head towards the prism. When holding the detector steady at 90 degrees, we zero the value. We now move the detector to the far side of the roll. We place the target back on the detector and adjust the projected beam so it hits the target. We hold the detector steady at 90 degrees, remove the target, and the value we see is the amount that needs to be adjusted by moving the roll. This can be done live time as we all watch. We're only interested in the horizontal value here and getting it to 0. The vertical value will go back to 0 once everything is tightened down again. This was all done using the values program measuring one roll. If you wanted to measure multiple rolls and get a PDF report, you would find the roll program in the main menu of the display. The equipment setup is identical to what we already demonstrated, so we would be ready to measure. First, with any alignment application, you would need to input the dimensions of what is being measured. As we've already shown, the first measurement step in the program is measuring and adjusting the first roll in the vertical plane using the digital level. Here you can adjust and move the rolls live time just as we did in the values program. With the digital level, the program shows you precisely where you need to be in both axes and the corrections that must take place to be within tolerance. Next, we move on to the horizontal plane of the first roll. The goal is to make sure the rolls are parallel with each other. Once again, the program shows you exactly where the laser beam hits the detector and where you need to move on the roll. In this case, we need to move the back end of this roll to the right, 1.74 millimeters, to get us into tolerance and square to our reference line. With the ability to do this live time, we can decide whether to adjust and correct the rolls directly on the screen or wait and compare the results to the other rolls. At the end of measuring, you can look at your results in tables and graphs comparing each roll and what the next steps are. At this stage, the E970 gives you the capability to change the initial reference point or roll. This allows you to choose the optimal move for you and your team. We understand it can take a lot of time to align your rolls during shutdowns or process changes, whether you do it yourself or have a service company do it with traditional and optical methods. This time is costing you production hours. With the Easy Laser E970, it saves you time and increases your production hours. As we have demonstrated, the E970 can be set up or bucked in with ease and in a short amount of time, even before the machine is shut down. This gives you the optimal time you need spent on measuring the rolls. Once the setup is out of the way, you can see there are many efficient measurement options available to you. One situation may occur where you save the reference measurements you have taken of the monuments on the floor. Next, you can take 2 points on the machine's frame, which will tell you how square it is to the reference line. This would give you another potential reference to work with. Then you can take the measurements of a set of 3 rolls, for example, without trying to adjust or move any, because the line must come back up. Maybe you're not satisfied with the results of the set of rolls you just measured, so you put them up in the boardroom, connecting the display or TV projector, and discuss with your team and pick the optimal move or roll adjustment by changing the reference points. This way, during the next shutdown or process change, you have a plan of attack and you have saved yourself some time. As long as the measurements of those 3 rolls have repeated, you can go in and correct the rolls of your choice. A week later, there will be another process change, but instead of making any moves that could affect the process of the product, you decide to gather more information. You measure the next 4 rolls you suspect are misaligned and analyze further before making any corrections. You are now mapping out the line in incremental steps, so that when the shutdown day does come, you have a plan on what you want to adjust. Imagine before you get to that maintenance day shutdown, you have to replace a roll, as the old roll is coming out. In this case, you can set up your laser to a roll close by and adjust the setup so that it matches the results you have in your program record. Now, set up the detector and move the new roll into place live time. This will save you a lot of time and money. In summary, some of the benefits of using the Easy Laser E970 roll alignment system include quicker and easier to set up than traditional optical methods. Keep the maintenance and service work in-house, saving money. Less production losses, increased production time. Less bearing and sealing wear, reduced vibration. PDF documentation and reporting can be produced directly on site. Keeps maintenance costs down and extends the service life of wear parts. Can be used for other geometric applications in addition to parallel, including straightness, flatness, and more. Thanks for watching.